Okay, my calculus friends, let's get some first things first. Position. Position is given us by this, usually S. I wasn't the one in charge of your position function. I probably would have called it P, but that's just because I'm a weirdo. They call it S. Position of some particle at time t is the position function. And then we have the positions function's friend, velocity, the velocity function. Okay, v of t, and it turns out that the velocity function is the derivative of your position function. Okay, so you're going to see me write that every single time we do a velocity function calculation, that the velocity is the derivative of the position. Okay, AP, the AP graders want to see that you know this connection, that velocity is the derivative of position. So we're going to write that every single time so that you let them know that you know what you're talking about. Whether you do or not, we're going to look like we do mathematically. And then we have our friend acceleration. Acceleration, one L or two L's in acceleration. Like that, acceleration. Two C's, one L, acceleration function. Well, the acceleration function is the derivative of velocity, which happens to be the second derivative of position. But that's going too far. All we have to do is stop here and saying that acceleration is the derivative of velocity. Okay, we don't have to say that it's the second derivative of position. But that's what we're going to do. So most of the time we have some type of a trigonometric function, right? One that is multi-differentiable, or a cubic or a fourth degree polynomial, one that is multi-differentiable. Okay, we rarely will start with a linear because that's only got one derivative and we're done. Okay, so some things about our derivatives. If your derivative is positive, right? If the derivative is positive, that means f is increasing. Right? If the derivative is positive, your function is increasing. That's one of our connections between f prime and f. For our position, that means our particle is moving to the right. It has positive movement in the positive direction, which is to the right on our x-axis. Okay, so if our derivative is positive, then f is increasing, right? The function itself is increasing, and our particle is moving right. What about if our derivative is negative? That means f is decreasing, right? The function itself is decreasing. But for our particle, that means it's moving to the left, right? It's still moving, but now it's going in a quote-unquote negative direction, to the left. Okay, so positive first derivative means you're moving right. Negative first derivative means the particle is moving to the left. And what about if our derivative is 0? That means the particle is at rest. It's not actually moving. Right, so in that case, we're going to have a horizontal tangent, right? We either have a local maximum or a local minimum for f. It's neither increasing nor decreasing. So if we have a first derivative that's 0, then your particle is at rest. Okay, it may or may not be changing directions. Okay, but usually, well, it has to. In order for it to change direction, it has to come to a complete stop. So that's something that must happen anytime we change direction from first derivative positive to first derivative negative. Okay, so that's all the good stuff. That's all the calculus, the underlying concepts behind our math that we're actually going to do right now. Okay, so we're told a particle moves along a horizontal line, so that's position given at positive times of t is this function, right? S of t is a nice cubic where s is measured in meters and t is in seconds. Must be a physics problem. Find the velocity at time t. So it wants the equation, right? It wants the equation for velocity, and then it wants what is the velocity at t equals 1. Okay? So the first thing we do with all of these position problems in AP Calculus is we write this notation. Velocity is equal to the derivative of position. Okay? We're asked about velocity, and we want to connect it to position. AP wants to know that you have that underlying level of understanding. Because the derivative's easy, right? Hopefully. The derivative is 6t squared minus 14t plus 4. So there's your function. So we're going to figure out what is the velocity at time 1, which means we're just plugging 1 in for t everywhere we see it. So 6 times 1 squared minus 14 times 1 plus 4 is, I believe, negative 4. Okay, which is good, right? It's okay to have a negative velocity. That just means we're moving to the left at time t equals 1, right? So that's what that means. Oh, B, when is the particle at rest? Okay, so let's do this. When is a particle at rest? The particle is at rest when the velocity equals 0. Right? Velocity is at rest, or sorry, particle is at rest when velocity equals 0. So we can even write that in here, when velocity equals 0. So we set our velocity equation, 6t squared minus 14t plus 4, equal to 0. So let's solve this, shall we? What might be your first step to solving this? I would want to divide everything by 2, right? Everything is an even number, so let's pull out the 2 that's well, I guess we can divide it by 2, it doesn't matter. 0 divided by 2 is still 0. 3t squared minus 7t plus 2 is going to be our equation that we're going to try and now factor. So we have as factors definitely a 3t as one factor and t as the other one. Now I'm looking for numbers that multiply to give me 2. Well, that's just 2 and 1. So I'm going to put a 2 and a 1 in these two places. And let's see, that means I need to have a 2 on this side and a 1 in that side. And they both have to be negative. Okay, so let me explain why. I need my O and my I to add up to be 7. So 3 times negative 2 is negative 6t, and then I have one more t for a total of negative 7t. And of course, negative 1 times negative 2 is positive 2. So these are my factors of 3t squared minus 7t plus 2. Now when I set each of them equal to 0 and solve, I get t of 1/3, and I get t of positive 2. So these are my 2 times where my particle is at rest, when velocity equals 0. So let's see, those are the times when the particle is at rest. Now let's see, when is it moving to the right? So we're going to do something that's not calculus approved, just so you know, and that's make a sign, do a sign analysis. So we put our 2 zeros, right, is 1/3 is one of our zeros, and 2 is another one of our zeros. Okay, so of course we're just talking about positive values of t, so we'll put 0 on here also. So we're going to see, is our graph positive or is our graph negative? Right, that's what we're looking for. When is our graph positive above the x-axis, and when is our graph negative? We know when it touches the x-axis, that's here and here. So let's see, we have a quadratic, and it's looks like it's a positive quadratic, so I'm pretty sure we could do a nice little graph like this, right? These are the 2 zeros. This is where our graph crosses the x-axis, which means that between 0 and 1/3, I have positive y values. Right? In other words, my derivative is greater than 0, right? And also from everything greater than 2, yes? My y values are also positive. In other words, my derivative is greater than 0. And then everything in between here, what's happening with the derivative? They are less than 0. So wherever my derivative is positive, my particle is moving to the right. Okay? So we're going to use complete sentences. The particle is moving right on the intervals from 0 to 1/3 and 2 to infinity, because f prime is greater than 0. Okay, so it's got nothing to do with our sign analysis, but everything to do with our derivative being positive. Okay, if our derivative is positive, your particle is moving to the right. Okay, that is our justification that we have a positive first derivative. Okay, let's look at our next question then. Let's move on here. Find the acceleration at time t and at t equals 1 second. So the calculus wants us to say that the acceleration is equal to the derivative of the velocity. Okay, that wants, AP wants you to make that connection, right? To link the acceleration with the velocity function. Acceleration is the derivative of velocity. So 6t squared minus 14t plus 4 becomes 12t minus 14. Okay, so that's the derivative of the velocity equation, 6t squared minus 14t plus 4. And it wants what is the acceleration at 1. So 12 times 1 minus 14 is -2. Okay, now this is going to be important in a couple of days, but notice velocity was negative at 1, and acceleration is negative at 1. And we're going to put these two things together because they have the same sign, because they're both negative. That means the particle is speeding up when t equals 1. Okay, so we'll talk about speeding up versus slowing down. If your first derivative and your second derivative have the same sign, then your particle is speeding up. But what direction is it going when it's speeding up? It's going to the left. Okay, so directional speed is what we're going to get to eventually. All right, find the displacement of the particle between 0 and 1.7. Looks like we're going to have a calculator. So we're going to go back to displacement is position. So we're going to find out what is s of 0. Okay, my equation was 2t cubed minus 7t squared plus 4t plus 5. And when I plug in 0, I get 5. Right, so the position of my particle at 0 is 5. So now we have to figure out what is s of 1.7. And I'm going to use my calculator to do this. So bear with me 1 second. So the displacement of the particle is what was the position at 0 to what was the position at 1.7. So 5 minus 1.396 means our displacement, which is just the change of position, is 3.604 units. Explain the meaning of your answer. Okay, so at 0, my position was at 5. And at 1.7, my position is at 1 point. So if we consider this like an x comma y, at 0, we're at 5. And after 1.7 seconds, we're at 1.36. Right? So position is, or rather displacement is the difference in between your starting and ending points. Okay, so we're just subtracting your end point from your start point. Here, switch that final minus initial. What happened down the road to where we started at?
It's not really the y value.
Okay, so then total distance traveled. Okay, total distance traveled is how far have we gone to the right? How far have we gone to the left? Maybe we've gone back to the right, right? So now we're looking at driving your total speedometer, right? If I drive from my house to school and then from school back to my house, technically I've gone 0 places, right? My displacement is 0. But my total distance traveled is however far it is from school to my house plus from my house back to school, right? That's the odometer on your car. Okay, so we want to do some other things. We need to figure out when it was going right and for how far, and figure out when it was going left. Okay, for our total distance traveled. So for distance traveled, right, the total distance, we have to figure out how far it's gone to the right. So according to part B, we knew that it went right between 0 and 1/3. Our graph was, our first derivative was positive. So it's moving to the right. So we calculate our position at 1/3, which was 5.63. So at 1/3, we are at 5.63. And then we know at 1.7, we're at 1.369. Okay, so we're moving left after 1/3 to 1.7. So we add together our two distances traveled to get a total of 4.864 units is the distance that we have traveled from 0 to 1.7. Okay, so this is what you need to remember, is that when the derivative is positive, you're moving to the right. When the derivative is negative, you're moving to the left. And when the derivative is 0, that's when your particle comes to rest and you're not moving at all.